Assalamualaikum students, welcome to Electronics. I'm Madam Rosmina Zwin Abdurrahim. As usual, before we go further, let's have a look on this hadith. The Prophet ﷺ said, O people, knowledge only comes by learning, and understanding only comes by seeking understanding. For whomever Allah intends good, He gives him understanding of the religion. Okay, I'm sharing this hadith because I would like to emphasize to you that as students of knowledge, we really need to put effort to really understand. We really need to put effort to learn. We need to put effort by asking Allah to give us the true understanding, okay, for us to get the knowledge, because Allah is Al-Alim, okay, all the knowledge is coming from Him. Now let's move to chapter 2, Semiconductor Materials and Diodes. Basically, chapter 2 is divided into few videos. So for this video, I call it as chapter 2A. We are going to cover two subtopics. The first one is on classification of materials, and the second one is on semiconductor types. Okay, let's start with the first subtopic, which is on classifications of materials. Okay, materials can be divided into three types, which are insulators, conductors, and semiconductors. Okay, so as you know, for insulators, these materials are with a very high resistance, which means current cannot flow. So for example of this material, such as mica, rubber, woods, glass, and so on. And for conductors, in contrast to insulators, is the materials with very low resistance, meaning current can flow easily. So for example of conductors are copper, aluminium, or any metals, okay, which are all good conductors. And the third type is semiconductors. These semiconductors can be good conductors or insulators. Before we go further, let's start with the basic atomic structure of a material. So as we know, an atom is normally composed of a nucleus and neutrons as well as electrons. Okay, then as we know, electrons at the outermost shell actually are called the valence electrons. Okay, talking about semiconductor materials are coming from group 4. Okay, so specifically we are talking about silicon and germanium. So as you know, they are from group 4, so meaning they have 4 valence electrons. Okay, then you should know that for an atom to be stable, it needs for 8 electrons, right, at its outermost shell. Then only the atom will be stable. So as we know, silicon have 4 electrons at the outermost shells, right? So meaning it needs for another 4 to become stable. Okay, so where do we get the other 4 electrons? Obviously from other silicon atoms nearby. Okay, so if you can see from here, we have 4 nearby silicon atoms. Okay, then this atom somehow will share the electrons. Okay, so this sharing of electrons is bound to a bond called covalent bond. If you still remember, okay, this is just like revision, I hope, to you guys. Okay, so we have one covalent bond consisting of 2 electrons, second, third, and fourth covalent bond. So altogether we have 4 covalent bonds consisting of 8 electrons. Okay, under this stage we say that the silicon atom is stable. One important concept in semiconductor that we have to know is band gap energy. In order for electrons to become free, they have to break the covalent bond. To do so, they require minimum energy, which is known as the band gap energy. Okay, so as we can see from this energy band diagram, the electrons that are confined to covalent bonds are here at the valence band. Once they acquire enough energy, it can be coming from temperature or surrounding, they manage to jump to conduction band, and here they become free electrons. Another concept that you should take note in semiconductor is how electrons or holes are moving in this semiconductor. So you imagine just now when electron becomes free, where they gain enough energy to jump to conduction band, right? So they become free. So what will happen when electron becomes free? So as you can imagine here, the first stage, it becomes free electron, right? So what will happen next? This slot will become empty. Okay, so after that, the neighboring electron somehow will move to fill the empty space. Okay, then now this space becomes empty. Then the next neighboring electron somehow will move to fill in the other space. So as you can see here, if we go further, you can see somehow actually electrons are moving from this side to here, to here, and to here. Okay, you can see one direction of electrons movement. Then in contrast, you can see that initially the empty space is here, right? Then after that it becomes here, then later it becomes here, then later it come to here. So as you can see here, the empty space, or we call it as holes, are moving this way, and in contrast electrons are moving this way. Now we come to the second subtopic, which is semiconductor types. Okay, for semiconductor there are two types, which are intrinsic semiconductor and extrinsic semiconductor. In short, intrinsic is a pure semiconductor, while extrinsic is impure semiconductor. For intrinsic semiconductor, it is a single crystal semiconductor material with no other types of atoms within the crystal, meaning it is a pure semiconductor. If we talk about silicon atoms, okay, so in the structure there are only silicon atoms are there. Okay, so that's why they are called a pure semiconductor. Then in this case, the densities of free electrons and holes are equal. Remember, we discussed about how electrons and holes are moving in semiconductor. So the moment we are having one free electron, okay, let's say the silicon atoms are being confined to covalent bond, remember? Okay, so let's say this electrons is it gains enough energy to break the covalent bond, they become free electrons, right? Okay, so the moment one free electron is created, we are also creating one empty space here. Okay, so you can imagine if we are creating 100 free electrons, at the same time we are creating 100 holes. So that's why it is said the densities of electrons and holes are equal. Okay, so the densities of this carrier, the carrier actually refers to electrons and holes. So the density of this carrier concentration actually can be calculated using this formula. Ni equals Bt 3 over 2 exponential negative Eg over 2 kT. And I is the intrinsic carrier concentration. Okay, B is the coefficient related to semiconductor material. T obviously is the temperature in Kelvin, and Eg actually is the band gap energy, while K is the Boltzmann constant. The value always will be given. Okay, so if we know the value of Ni, okay, straight away we know the densities of electrons as well as the densities of holes. Remember before this we discussed about band gap energy, right? Where actually band gap energy can be given as energy at conduction band minus energy at valence band. Okay, so it will give us the Eg, the band gap energy. So for different semiconductors, it has different band gap energy value. For example, silicon, it has 1.1 electron volt, germanium 0.66, and another type of semiconductor, gallium arsenide, is 1.4. What does it mean? It means that for silicon, we require for 1.1 electron volt for an electron to be able to break the covalent bond to be able to become free electron. For germanium, we require at least 0.66 electron volt for electron to become free electron. The same goes to gallium arsenide. Okay, then if you see this energy band diagram, it's the same thing where in order for the electron to become free, it needs to jump from valence band to conduction band. And we have the Fermi level. Fermi level for this case normally is at the middle between conduction band and the valence band. Okay, this is one example for intrinsic carrier concentration calculation, the Ni. Okay, we are supposed to calculate Ni, and all the values are given, the band gap energy as well as the Boltzmann constant value. So in this example, what we have to do is we have to calculate the Ni value using the formula. Okay, so as you know, Ni is given by this formula. You substitute all these values and the answer is Ni equals 1.5 times 10 to the power of 10 over centimeter cubic. What does it mean? It means that you imagine in 1 centimeter cubic, okay, there are 1.5 times 10 to the power of 10 of free electrons. And at the same time, we also have 1.5 times 10 to the power of 10 of holes. Okay, because remember in intrinsic, the density of electrons and holes are equal. Here is another example, but it's just using the same formula. It's just that for this example, we are supposed to find for the Ni value, which is the intrinsic carrier concentration for gallium arsenide at T equals 300 Kelvin. So in this case, you know that for gallium arsenide, the band gap energy is given as 1.4 and the Boltzmann constant value is given by this value. It's not Boltzmann, it's the B value, but the Boltzmann constant is the K value given by this constant. Okay, so again, you just substitute using the same formula. Okay, I leave it for you to do on your own. If you solve for this, you are supposed to get the intrinsic carrier concentration is 1.8 times 10 to the power of 6 over centimeter cubic. Again, what does it mean? It means that in 1 centimeter cubic, okay, there are 1.8 times 10 to the power of 6 of free electrons, as well as there are 1.8 times 10 to the power of 6 of holes. Remember, both densities of electrons and holes are equal in intrinsic carrier. Okay, here is another example. The same thing, you just use the formula, substitute the values accordingly. You are supposed to get the answer. In this case, this is the answer. Now we come to extrinsic semiconductor. Okay, as I mentioned before, extrinsic semiconductor is an impure semiconductor. It's not pure anymore. Okay, but first, why do we need for this extrinsic semiconductor? Basically, in intrinsic semiconductor, the Ni value, remember the Ni value that you have calculated before, it is very small, meaning since the density of free electrons are very small current is possible. Okay, in our electronic device, obviously we want to have significantly higher current. So in this case, since the current is very small in intrinsic, we have to increase the number of carriers in order for us to increase the free electrons so that higher current is possible. So how to increase the number of carriers? We can add impurities to our semiconductor. It could be to our silicon or germanium. So these impurities can be from group 5, okay, so that the semiconductor will become n-type, and or it could be from group 3 where the extrinsic semiconductor will become p-type, which I will explain in next slide. Okay, for n-type, which is negative type, as I mentioned just now, it is added with impurities from group 5. So as we know, group 5, they have 5 electrons at the valence as the valence electrons. It means there are 5 electrons at the outermost shell. For example, materials from group 5 are phosphorus and arsenic. So you imagine if you dope or if you add phosphorus to silicon atom structure. So remember, silicon has 4 valence electrons, so phosphorus has 5 valence electrons, right? So it contribute 1 electron here, another one here, another one here, and one here. But since it has 5 valence electrons, we have one additional free electrons. Okay, so the fifth electrons is loosely bound. Okay, it becomes free electron. Okay, so as you can see, at this moment there are no holes are created, right? No holes are created. Whenever we add it with impurity, in this example phosphorus, one free electrons is being introduced, is being added to the structure. So meaning to say, even at room temperature, this electron has enough energy to break away and becomes free electrons, because we add it with impurity. Straight away we put one phosphorus atom, we are creating one free electron. If we put 100 phosphorus atom, straight away we are creating 100 free electron. If we are putting 1000 phosphorus atoms in this silicon structure, we are creating 1000 free electrons. Okay, so because of that, atoms from group 5, which are phosphorus and arsenic, are known as donor impurity. Why donor impurity? Because it donates electrons to the structure. So in this case, whenever we dope it or we add impurity from group 5 to our semiconductor, this semiconductor becomes negative type, n-type semiconductor, because it has extra electron which is negatively charged. On the other hand, for p-type semiconductor, p-type is positive type semiconductor. The silicon structure, the semiconductor, is doped or is added with impurities from group 3. So as we know, for group 3, it has 3 valence electrons. Okay, examples are boron or aluminum. Okay, then since it's coming from group 3, so imagine if you dope it with boron, you add impurity of boron here in the structure. So we have one electron here, the second one is here, the third one is here. But since boron only has 3 valence electrons, the fourth one becomes empty space, no electrons. So we can say we have extra hole in the structure. So can you imagine, whenever you introduce one boron atom, we are introducing one extra hole in the structure. So if we put 10 boron atoms, we are giving 10 extra holes to our silicon structure. If we put 1000 boron atoms, we are having 1000 free extra holes in the structure. So once extra hole is created, the valence electrons from outer shell are attracted to fill the holes, okay, added by this boron. Okay, then it will cause the movement of holes. Okay, so atoms from group 3 are being called acceptor impurity. Why? Because it accepts electrons. It has empty space here, remember the extra hole. So this extra hole is willing to accept electrons from the neighboring atoms. Okay, so that's why it is being called acceptor impurity. So if the impurity is coming from group 3 to be added with our semiconductor, it becomes p-type, positive type. Why? Because we are having extra hole which are positively charged. Okay, in terms of energy band diagram, remember just now we discussed about the intrinsic semiconductor, where we have the valence band, conduction band, and the Fermi level is in the middle. Okay, now if we are considering n-type semiconductor, the negative type semiconductor, we are going to have a new band gap. Okay, meaning because we are having impurities, remember we are adding with the structure with impurities, the donor impurities, so somehow the band gap is being modified. Now we introduce a new band gap which is closer to conduction band. In contrast, for p-type semiconductor, the positive type semiconductor, the band gap also is being modified, but now the Fermi level is closer to the valence band. Okay, so the idea is the Fermi level for n-type and p-type. For n-type it is closer to conduction band, for p-type it is closer to the valence band. Talking about extrinsic semiconductor, the densities of electrons and holes are not equal anymore. Okay, you should take note, in extrinsic, the densities of electrons and holes, they are not equal anymore. It's not like intrinsic. Okay, then you should also take note that whenever we add impurities, we call it as doping. Doping meaning we add impurities to silicon structure. So by doing that, we can control the concentration of free electrons as well as the holes. Okay, so by controlling these carriers, the electrons and holes, actually we can control the conductivity and currents in the semiconductor. Okay, in intrinsic, this formula is important. N naught P naught equals Ni squared. N naught is the thermal equilibrium concentration of free electrons. Okay, P naught is the concentration of holes, while Ni is, remember, Ni is the intrinsic carrier concentration. So you should take note, N naught P naught equals Ni squared. Okay, for n-type, the negative type, okay, remember I was saying just now, we introduce one phosphorus atom, we are creating one free electrons. We introduce 1000 phosphorus atoms, we are creating 1000 free electrons, right? So obviously for negative type, n-type, the electrons are the majority carriers, meaning the structure are full of free electrons compared to holes. Okay, so in this case we are saying n-type, for n-type electrons, they are the majority carriers. Obviously, holes are the minority carriers. Meaning electrons are much more compared to holes. Okay, so for n-type, remember we have n naught p naught equals ni squared formula just now. Okay, so generally in n-type semiconductor, remember we dope it with phosphorus. For example, with phosphorus atom, impurity atom, remember? Okay, so as I was saying, one phosphorus atom, one free electron, 1000 phosphorus atom, 1000 free electron. So that's why we can somehow approximate that the concentration of free electrons, which is N naught, approximately equals to the concentration of the donor atom. Okay, I think you will understand better when we do the example. Okay, so once we say that N naught approximately equal to ND, straight away we can calculate for P naught from this formula. So P naught becomes Ni squared over ND. Okay, the same goes to p-type, positive type, where holes now are the majority carriers in p-type. Remember, one boron is creating one hole, 1000 boron are creating 1000 holes. Remember, so holes are the majority carriers. Then obviously electrons now becomes the minority carriers. Okay, then it's about the same thing. Whenever we are considering the concentration of holes, we can approximately say that it is equal to the concentration of acceptor impurity. Okay, then from N naught P naught equals Ni squared. okay, we can modify the equation, where from there also we can calculate for the n naught, the concentration of free electrons equals to Ni squared over Na, which is actually the P naught value. Let's have a look on this example for you to understand better. Okay, in this case, it is mentioned that silicon is being doped with phosphorus. Okay, so if we talk about phosphorus, we know it is from group number 5, meaning we are talking about n-type semiconductor, isn't it? So it is doped with Nd, the donor concentration of 10 to the power of 16, and Ni value is given. Okay, in this case, you are supposed to calculate the concentration of electron and holes. So remember, in n-type, the majority carriers are electrons, right? While the holes become the minority carriers. Okay, so in this case, we can say that the concentration of electrons is approximately equal to the concentration of donor impurity. Remember, one phosphorus atom is creating one free electron. 10 to the power of 16 phosphorus atoms are creating 10 to the power of 16 of free electrons. Okay, that's what I mean. Then obviously, once we know the n naught value, we can straight away calculate for P naught, where P naught equals to Ni squared over Nd. Ni is given, Nd equals to n naught just now, so straight away we can calculate for P naught. Okay, so as you can see from here, the concentration of holes is 10 to the power of 16, while the concentration of electrons and not the concentration of electron is 10 to the power of 16, while the concentration of hole is about 10 to the power of 4. So it is agreed with this saying that electrons, they are the majority carriers, so that's why the concentration is much higher compared to holes, which are the minority carriers, so that's why the concentration is just 10 to the power of 4. Okay, here is another example where you have to calculate the majority and minority carrier concentrations for silicon. Okay, if it is doped A with Na acceptor impurity, okay, with concentration of 10 to the power of 17, for case B, where it is being doped with donor impurity with a concentration of 5 times 10 to the power of 15. Okay, so first thing first, because we know that n naught P naught equals Ni squared, right? So we need to know the Ni value first. So first thing first, we calculate for Ni. Since we are talking about silicon, okay, we use this value and this value to calculate for Ni. Then later, once you know the Ni value, we consider for part A, where Na is 10 to the power of 17. We know that it is referred to P-type. Why? Because it refers to acceptor impurity. Group number 3, remember? Okay, so we are talking about P-type semiconductor here. For part B, Nd is 5 times 10 to the power of 15, so it refers to the donor. D refers to the donor impurity, so we know that it is related to n-type, negative type, because it is doped with group number 5, the donor. Okay, so how to solve for this? You know that for p-type, we are talking about p naught as the majority carriers, right? The concentration of holes. So P naught actually approximately equal to Na, which is 10 to the power of 17 in centimeter cubic. So once we know the value of P naught, straight away we can calculate the value of N naught, where N naught equals to Ni squared over P naught. Okay, so the same thing for part B, we know it is n-type, so the majority carriers are n naught, which is approximately equal to Nd, right, which is 5 times 10 to the power of 15 over centimeter cubic. So from there we can calculate for P naught, which is Ni squared over N naught. Okay, so you can try to do on your own because the answers are being given. Okay, here is another example. Okay, it is being mentioned that this silicon is doped with arsenic atoms. Okay, the question is asking whether this is N-type or P-type semiconductor. So you know it is arsenic, right? Okay, arsenic comes from group number 5. So we know here we are talking about N-type semiconductor. Okay, the next part is asking for us to calculate for electrons and holes concentration. So I think it's just the same. First we need to calculate for Ni, then use the N naught P naught formula for you to calculate for electrons and holes. Okay, so try to do on your own because the answers are also given. Okay, so let's recall what we have covered so far. We have covered subtopic 1, the classifications of materials is related to semiconductor materials and properties. Then the subtopic 2 refers to semiconductor types, which are the intrinsic and extrinsic semiconductors. So I think that's all. We are going to continue another 2 subtopics in next video. Okay, thank you. Bye.